Hello, my name is Elena Lorenza from the Institute of Solar Energy from the Polytechnical University of Madrid. I am going to present very briefly the paper titled A Comparative Economic Feasibility Study of Photovoltaic Heat Pump Systems for Industrial Space Heating and Cooling. This paper has been published in the journal Energies and is co-authored by me, Luis Narvarte, and Ana Belén Cristóbal. This paper has been open peer-reviewed and is fully open access. The objective of this work is to compare two technical solutions, one with a self-consumption configuration and another one with an autonomous configuration, in terms of economic viability. The self-consumption configuration is composed of a heat pump that is powered by the national grid and by a photovoltaic generator through a grid inverter. This grid inverter also allows for the injection of the photovoltaic surplus into the grid. In the autonomous configuration, the heat pump is powered by a photovoltaic generator and a diesel group through a frequency converter. We have also added a thermal energy storage for giving the solution bigger flexibility. This study has been performed for supplying the electricity consumption needed for the heating and cooling of two animal farms, a rabbit farm and a poultry farm. Two different photovoltaic structures have been considered, a static structure and a north-south tracking structure. For the economic viability analysis, we have calculated the profitability index. The profitability index is the net present value of the system normalized to the initial investment cost. By definition, an economic investment is viable if the profitability index is at least bigger than 1. We can see in the figure how the profitability index is actually bigger than 2 for all the cases that we have considered here. The bars framed with discontinuous lines correspond to self-consumption configurations, while the bars with continuous lines correspond to autonomous configurations. It is easy to see how autonomous configurations present higher profitability indexes than the self-consumption ones. The reason is the importance of the economic savings in the electricity bill. With self-consumption configurations, the economic savings are only in the terms of energy consumption. On the other hand, autonomous configurations allow for these economic savings to be total. We eliminate both the terms of access to power and of energy consumption. We have also calculated the internal rate of return, that is, the interest rate that makes the net present cost of the system equal to the initial investment cost. For an economic investment to be viable, the internal rate of return needs to be bigger than the national interest rate. In Spain, this interest rate is 0.81%. We can see in the figure how all the internal rates of return are at least 10 times the national interest rate, so all the systems present very good profitabilities. Once again, autonomous systems present higher profitabilities than self-consumption ones. Finally, we have calculated the payback period, which is the time needed for the symmetry of the annual cash flows to be equal to the initial investment cost. In this study, we have considered a lifetime of the photovoltaic heat pump system of 25 years. And we can see how the payback periods for all the systems considered are less than half this lifetime of the system. Besides the economic viability analysis, we have calculated the levelized cost of electricity of all the photovoltaic heat pump systems here considered. And we have compared it to the levelized cost of electricity of a traditional grid-powered system without any photovoltaic generation. The worst case presents an autonomous configuration with a static structure. It presents a levelized cost of electricity of 7.46 cents per kilowatt hour. This implies a savings of 57% compared to an only grid-powered system. The best case presents a self-consumption configuration with a tracking structure. The levelized cost of electricity is of 4.74 cents per kilowatt hour, implying savings of 70% compared to an only grid-powered system. Now, self-consumption configurations present better results than the autonomous ones. The reason is that now the economic savings in the electricity bill are not so important. The most important factor is the electricity production achieved by the photovoltaic system. We can see how in the worst case, the energy yield is less than half the energy yield of the best case. Finally, the economic viability of photovoltaic heat pump systems has been proved by means of the Profitability Index, the internal rate of return, and the payback period. Autonomous solutions present better results than self-consumption ones because of the importance of the economic savings in the electricity bill. On the other hand, photovoltaic heat pump systems imply levelized cost of electricity savings between 57 and 70% if compared to an only grid-powered system. Now, self-consumption solutions present better results than the autonomous ones because of their higher energy production. Finally, the robustness of the results has been demonstrated by means of a sensitivity analysis. If you are interested in learning the details of this work, you can find the paper in this link. I hope you find it useful. Thank you very much.